Hey everybody. So we're going to look at another topic now. Uh, it's called transformation of functions, um, or transformations of functions. There'll be multiple transformations we'll do. In any event, so let's just start this with a simple example. But let's just a little background. One of the points of transformations is it's a way to understand functions and a way to manipulate functions that lets us um, kind of leverage what we know about simple functions so that we can get some information, some more complicated information without having to do as much work. Another way to say it, let me be more clear. Like we have these toolkit functions. For instance, I'm looking at f of x equals x squared. Right? This is a very basic, simple function, but we can understand some things about it. Um, we use functions, scientists use functions to model something, right? So they're looking at some little piece of the universe that they want to study, and they use a function to describe that piece of the universe and make predictions about that piece of the universe. And maybe x squared doesn't describe perfectly their little piece of the universe, but maybe something related to x squared does. And if we find that related function through transformations, without having to do a bunch of extra work, we will already know a lot about how it behaves because we know a lot about how x squared behaves. So that's kind of where these things end. It'll be a little bit of work to get there. So anyways, let's start with this example. So what I want to do first is just plot some points from this function. I'm letting Desmos do it for me, right? But all I've done is compute various values, right? If I take f of -2. I compute that as -2 squared is equal to 4. This gives me the point, right? The input -2 and the output 4. And so I've let my grapher do that for me. We can see this point right here and a few other points that are then graphed on our axes right here. So we've got our points, and if we continue to graph points, we could fill in and get the familiar graph of a parabola. Just wanted to highlight those points for this next part. Because what we're going to do next is we're going to take this function f of x and create a new function. Okay? And the way we create this new function is I'm going to do this. Right? It's like we're adding an instruction to f of x. F of x was the function that said, take an input, square it, give us back that output, right? So now we've added the instruction, take an input, subtract 1 from it, square that, and give us back the output, right? And so this is a new function. We could give it a name if we wanted to. And I want to look at the difference between this new function and our original function, right? So if we do the same thing, if I do something like g of -2, that means f of -2 minus 1, or f of -3, and we are squaring that, so -3 squared gives us 9, right? So notice the original function, we put in -2, out came 4. The new function, we input -2, out comes 9. Let's do one more here. If we input -1, we get f of -1 minus 1, which is f of -2, which is -2 squared, which is 4. So g of -1 is the same as f of -2 because we're taking that, we're adding that extra instruction to subtract 1. And so graphically what that means, let's look at these points on the graph. The ones in particular I want to look at are these two. The blue dots are our new function, okay? And that what we just noticed is that when we input -2, the output when we input -1 into our new function, we got an output equivalent to the input of the original function at -2. Let's do one more of these. Let's look at g of 0. This is f of -1, f of 0 minus 1, or f of -1, or -1 squared, or 1, right? So the output when we do g of 0 is the same as the output of f of -1, right? On our graph, that's these 2 points. This is the input -1 and the output for f was 1. The input of 0 also gave us 1 for this new function that I called g of x, right? It's as if, let's see if I can do this. Let's use a different color. Sorry, let's use, all right. It's as if we've moved these points to the right, right? The graph, the same outputs are now occurring 1 unit to the right. Every single point moves over. And if we add the entire graph here, right, we see that this graph is shifted over to the right. And that's the point of transformations, right? So now I've got a new function. It's very similar to the square root function. Remember how to clear all my drawings. I don't want those there anymore. Right? It's very similar to our original function. It's just moved over very slightly to the right. And so any information we have about the original function x squared, for instance, the fact that it was minimum at 0. When you input x of 0, you get the minimum of that function. Well, now I know the minimum is going to happen 1 point to the right, which is at x equals 1, right? Now, this is a very simple example. That was pretty self-evident just by looking at it. But when things get more complicated, that's the kind of information. We can take information starting from our original simple function and learn something about our new, more complicated function from it, okay? So let's do one more very similar idea. So let me take this one away. Now I'm going to consider what would happen. Let's make a new function, h of x. Let's move this up a little bit. H of x, I'm going to take f of x, the original function, x squared, and add 1 to it. All right, so now think about what this is doing. In the previous new function, I added an instruction at the top of our instruction. So f's instructions are take an input, square that input, output the result. Then we added the line, take an input, we added subtract 1, square it, output the result. H of x takes an input, squares it, it does what f does, and then it takes that and adds 1 to it. So it's like we're inserting a line after our original sets of instructions, right? So let's just think through what that would do. We're gonna spit out all the same values of f with this first part of the function, but that last instruction is going to make all of our output values 1 unit bigger. And so what that will look like, all of these points, the green points are our new graph, are the old points just shifted up once. And we see a graph that's all shifted up 1 unit, okay? This is a different way that we can transform a function, right? And we see that, again, it's very related to what we started with, but with just a simple little change, we can, describe something slightly different. Okay, let's look at something a little bit different, a little more complicated. All right, here's the function x cubed plus x squared minus 2x. We don't need to worry too much about what it is. I want to think about this a little more abstractly. I graphed a few points here. Let's think about this point here for a second. Okay, now I'm going to consider. So we've got our original function g of x. I'm going to consider what would happen if I multiplied the input by 2 before handing it over to g, right? So g of x is our, let's just say it once, is our set of instructions that says take an input, cube that input, square that input, and multiply that input by -2, and then add those 3 things together, right? So it's a little more complicated set of instructions. This new function, g of 2x, is saying take an input, double it, then cube that, square that, and multiply that by -2 and add those 3 things together. So it still does all that stuff that g did, but it just has this additional first step of doubling the input, right? Let's think about what that's going to do to our graph. For example, let's think about the input 0. When we input 0 and the first thing we do is double it, we get 0 back. So that point shouldn't change, right? Then we're just going to do what g does. So that point shouldn't change. If I input the number 1, the first thing we do is double it, and we get back, and we get 2, and then we do what g does. So when we input 1, the output will be what g did previously at the input 2, right? We get to that 2 sooner. We don't have to input 2 to get the output for 2. We input 1 to get the g's output for 2. So that 0.28 is going to come sooner. It's going to come at the value of x equals 1. So let's put that up here, right? The input, the new input at 1 gives us the output that we used to get at 2, right? Similar thing happens down here. The input at 1/2 was the input we used to get at 1, because we input 1/2, we multiply by 2 to get 1, then we hand it to g, so it does what g does there. And we get a similar thing here. And the overall effect of that is we have squished our graph in. We're getting to the values sooner. If you think about like starting at 0 and moving through the x values to get outputs, we get to the same output sooner because it's like we've doubled our speed. We don't have to wait until we get to the number 2 to get the output for 2. We get to the number 1, it gets turned into a 2, and we get the output for 2. So we get it sooner. And so our whole graph gets squished in, right? We say compressed horizontally. Okay, let's do one more example with this function. Now, instead of multiplying the input by 2, let's multiply the output by 2, right? And again, if we think about sets of instructions, that the g of 2x, the first example, the previous one we did, the new instruction came first, right? We always take our input first, but then we inserted this line to double the input before we do all the g stuff. Now, 2 times g of x means take an input, do all the g stuff, then double the output. Okay? So again, let's think about what that means for our individual points. There's 3 points here that have zeros as outputs. Well, when we double those, we're going to get zeros again. Nothing's going to change about those points, right? But for the points that have outputs that are not 0, when we double them, they're going to get bigger, right? 2 times 2 is going to be 4. 8 times 2 is going to be 16. And so those points are going to be twice as far away from the x-axis as they were. So let's look at this. So notice, right, a lot of our points just landed right on top of the original points because doubling 0 doesn't change anything. But here, -1 had the output of 2, but now -1 gives us a 4 because we double it. That input of 2 gave us an 8. Now that input gives us a 16. And when we look at that for our entire graph, what we get is a graph that is stretched vertically, right? We pull away from the x-axis. So if a point is already below the x-axis, like these points down here, right? Then when we pull away, we get twice as far away, right? So if you look closely, these are the same inputs, and the green one has twice the output, -0.6 to -1.2, right? And every point does this, pulls further away. So we've stretched vertically. So let's look at all of these things together now. Here's an arbitrary function. It doesn't really matter what this function is, but I just want to go through all of these. Let's write this down, what all these different transformations do. So I'm starting with the function y equals, I'll call it capital F of x. And I'm going to collect all the things we just did in the following way. We're going to have a new function that's going to be a series of transformations on f of x. Actually, let's just use little f because I think that's more familiar and that helps. So our new function, let's call it g of x, is going to be a series of transformations on f of x. And the way I'm going to write this is like this. So I'll explain everything when I finish writing. There's 2 different ways to write this. Let me just see what I did. I don't want to do it that way. Okay. Sorry, I had a change of heart about how I was going to write something. It doesn't really change any of the content, just how we explain it. So for now, I'm going to write it this way. So let's think about all the things we just did. One of the things we did was add or subtract in our case, right? So we just think C could be positive or negative inside our parentheses. So that's what this plus C is, that first thing we did. We also multiplied X, so that's B is representing that. We multiplied the function as a whole, that's what A does, and then D was adding to the output when we're all done. So those are the four things we just did, right? And we can do more than one of them at a time. For instance, right, I could think of A, that thing multiplying the whole function. Remember, we just looked at this and it stretched or compressed our function vertically, right? By multiplying by a big number, we're stretching it. If I multiply by a small number, we're compressing it vertically. It's getting closer. Notice if I multiply by a negative, it flips it over. So that's one kind of transformation we could do. B, that's multiplying the input. Just like multiplying the whole output stretches vertically, multiplying the input changes things, stretches or compresses horizontally. So for instance, I could compress this function like this. C, that was shifting things around horizontally. That was the first one we did, so I could shift my function a bit. And then D shifts it vertically. So by combining these functions, notice I get a very different function. It does a lot of things differently. The domain has changed, the range has changed, the size of the range in the domain have changed. Let's even throw in a negative to really switch this thing around. It's in a different direction, but it's still very related. You can see that a lot of things are similar about it. And if we knew a bunch of stuff about the original function, with enough practice, we would be able to understand a bunch of stuff about this new function very easily. Okay, so that's one of the points of these things. So let's go through each of these transformations and just write down exactly what they do. All right, so just getting back to our original, let's talk about what A does. A is multiplying the outputs by a number. And this, we said, was a vertical stretch or compression. And it'll stretch it, it'll make it bigger when the number we multiply by is bigger than 1, and it'll compress it when we multiply by a number that is less than 1, or more specifically between 0 and 1. And we should also put in here that a negative reflects over the x-axis, right? So let's see all this in practice. Here's my function, and I multiply it by a number bigger than 1. We're stretching it further away, right? There it's multiplied by 10. It's quite stretched from the x-axis. Back to 1, we're at our original. If we multiply by numbers less than 1, but positive, we're compressing it. Now we're multiplying by 0. That's kind of the boring option. It just kills the function. But if we multiply by negative numbers, but they're between 0 and -1, so in magnitude, they're less than 1, we're compressing it, but we're also reflecting it over the x-axis. There's a -1. It's a perfect reflection over the x-axis. And now we get the reflection plus a stretch for numbers that are negative, but larger in magnitude than 1. Below there, so they're less than -1. All right, so that's what our A value does. Let's get this back to 1. B, remember, this is multiplying the input. This is going to be a horizontal stretch or compression. And negatives will reflect over the y-axis. However, something interesting happens here. For the value of A, if we multiply by a number bigger than 1, we stretch it. That makes sense to us. We're multiplying by a number, things get bigger. And we'll see this is true for both B and C. The numbers the shifts, the transformations that we're dealing with inside the parentheses that are transforming the input, they do like the opposite of what we might think. What I mean by that is if I multiply x by a number bigger than 1, my graph gets smaller, right? It does the opposite of what I think. And if I multiply by a number less than 1, my graph stretches, right? And then for negatives, it's the same idea as before, right? Numbers that are bigger in magnitude than -1, further than 1 from the origin, make it smaller and flip it over the y-axis, and then small negative numbers stretch it out. Okay, so it's a very similar idea, these two stretches, but we get this reversal of when does it get bigger and when does it get smaller. All right, let's go on to C. This is adding, and this is adding to our input. So again, this kind of does the opposite of what we think it's going to do. Remember the very first function we looked at. The first thing we did was subtract 1, and it moved to the right. Oops, sorry, let me turn this one off. There we go. Whoops. So that original red dotted graph is there, and then the blue graph is it shifted to the right. We subtracted 1 and we moved in the positive direction, right? It's kind of opposite of what we might think is going to happen. All right, I'll turn all this off now. Okay, so with this function here, it's the same idea. Here I'm adding numbers and I'm moving in the negative x direction. And if I subtract numbers, I move in the positive x direction, right? So inside, working on the input, things do the opposite of what our expectations might be. And then finally, we have, let's write that down. Let's see, is a horizontal shift. And then finally, we have D, that's adding when we're all done, and that's a vertical shift. Right? And that does exactly what we expect because we're working on the outside, on the output of the function. If we add to our output, the graph gets higher. The outputs are higher values, and if we subtract, we get lower values. Okay, those are our transformations, right? And by combining them, we can really move our functions around quite a bit. There's one other piece to this puzzle, at least. There's lots of pieces to this puzzle. One other big piece I want to talk about, which is combining our functions, our transformations. So when we do this, we can think about. I like to think about where points end up, where points move when we do this, and so let's look at. Let's see. There's a nice one. This point, -1.5. If I, let's do a stretch and a shift horizontally. So I'm going to stretch horizontally. I'm going to stretch it. I'm going to multiply by 1/2, which makes it twice as wide, and then shift by 1 to the left. Okay. So let me write this out. We have our original function, f of x. And now I'm comparing that to, let's see, what did I do? I multiplied the x by 2, or by 1/2 x, and I added 1. Okay, that's what I did. There's a question of what order should we do this in, right? Because let's just think about what would happen depending on which order we do this in. So we're starting with this point. I'm going to start with the point -1.50. All I'm going to worry about is where that point's going to end up. So I have two things happening. I have a horizontal stretch. Things get twice as far from the y-axis. And I have a horizontal shift to the left. Isn't that what I did? Yeah, okay. Yeah, horizontal shift to the left. Sorry, I'm forgetting which graph is the original. I got really confused for a second. Okay. So if I started with this point, -1.50, and first I did my horizontal compression, horizontal stretch, it would end up twice as far away, right? So negative 1.5 would go to negative 3. And then I would shift one more unit. So we'd end up at negative 4. But that's not where we ended up. We ended up at negative 5. And so the order we should have done it in is we should first do the horizontal shift. So we shift negative 1.5 by 1 unit. So negative 1.5 goes to negative 2.5. And then we double that to get to negative 5. And that's where we ended up. Okay. So there was just to illustrate that depending on the order we do things, if I went negative 1.5, doubled it, moved it twice as far away, and then shifted one more to the left, we don't end up at the same place. So the order matters. And the rule of how you have to do things is simply that inside, remember this notion that inside the parentheses, things we do to the inputs, everything is reversed. That's, I think, the best way to think about it. And in this case, what I mean is the order of operations is reversed. We're multiplying x by 1/2 and then adding 1. If we're doing algebra, that's the order you think about it. If you give a number to x, you multiply by 1/2 and then you add 1 to it. When you're doing your transformations for the things we do inside, we go the opposite. First, I deal with the addition, adding 1, and I move 1 unit to the left, and then I double it because of that 1/2. And we'll end up in the right place. So that's our rule for inside the function. Outside the function, things like our vertical transformations, we follow the order of operations. So for example, if I do, let's just do something like 2 f of x minus 3. Right? And let's think about one of our points and try to figure out where it's going to end up. So there's the point 2, 7. So if I go in the order of operations, I'm thinking about, we're operating on the output. The first thing I'm going to do is double it. So the output 7 should go to 14. Then I'm going to subtract 3. So we'll end up at 11. So this point, our value at 2 should go from 7 to 14 and then down to 11. So let's see if that happens when I put in these transformations. So I'm multiplying by 2, so that's the value 2 for A. And notice our output is now at 14, and then I'm going to subtract 3. So I'm putting in a negative 3, and we end up at 11, just as predicted. So in the same way that the transformations do what we expect, bigger numbers make things bigger, smaller numbers make things smaller, positive numbers move in the positive directions, negative numbers move in the negative directions, we also follow the order of operations in the correct way. Inside the function, operations on the input do the opposite. We go reverse order of operations when we're doing more than one transformation, and so bigger numbers make things smaller, and smaller numbers make things bigger. Positive numbers move us in the negative direction. Negative numbers move us in the positive direction. So once we just get this idea that inside is reversed, it all kind of starts to make sense, right? It's difficult, I think, to understand why. It took me a lot of time of playing with functions and inputting things to kind of see what was happening and playing around with algebra. I think we just need to have these rules in our head, and the more we play with them, we can start to understand exactly why this is happening. Okay, that is going to be it for this one. Thanks, everybody.